Okay, so
yeah, so welcome everyone. We have our talk today by Gilberto, who unfortunately couldn't make it in person, but still here to tell us about triple Higgs production in the SM and in BSM at proton-proton colliders. So please go, Gilberto, and I'll interrupt when you have about 5 minutes left.
okay, so it says so I have 45 minutes or
50 minutes or so.
okay, cool.
Feel free to go for.
Okay, so let me close a bit the door. Yeah. Well, hello everybody. So yeah, so thanks a lot for the invitation. Unfortunately, I was not able to be there in person, but it's nice that this can still happen virtually. So I'm going to talk about triple Higgs production in proton-proton colliders. So this talk is based on two papers. So I did with Andreas and Professor Marco and Professor Robbins. So the papers are here. The archive numbers of the papers are here. Okay, so I am based at the University of Siegen. This is actually where I am now. And let's start then. All right, so this is the standard model potential for the Higgs. So this side represents the Higgs doublet in the standard model. After spontaneous symmetry breaking, the potential can be written in this way. So then we have the mass term for the scalar. This is the Higgs scalar. You have the self-interacting terms, the cubic self-interacting term, and the quartic self-interacting term. Okay. So the mass and the couplings that appear here are given as described in these equations. All right, so nothing special here so far. Now, in a proton-proton collider, these are the mechanisms for producing triple Higgs. Now, what you look at in this case as how likely, the first thing you have to look at this is how likely is to produce this state, triple Higgs state, considering the center of mass energy and the cross section. Well, the cross section already tells you what is probability of production actually. So if you consider the high Lumi LHC at 14 TeVs, the cross section for triple Higgs production as in the standard model is extremely low, okay, 0.05 femtobarns. In terms of events, this translates into about 100 events. So the situation is hopeless. You will not see this in the high Lumi phase of the LHC. Okay, then you may think, what would happen if we go to the future and we think for instance in the FCC. Now you have more energy in the center of mass, so 100 TeVs. So you can think also in a luminosity of, for instance, 10, 20 inverse attobarns. And now the cross section gets higher, so it increased by a factor of 100. Instead of 0.05 femtobarns, now you get 5 femtobarns. And in view of this luminosity, you can produce about 100,000 events. So now the situation is more promising. Again, this is as in the standard model. There is nothing else happening. So why are we interested in studying triple Higgs production? Well, this is a way to prove for new physics, of course. So you see deviations in the expected production with respect to the standard model. And these values are in tension at a significantly meaningful level, then this can be a way of finding new physics. Also, triple Higgs production is sensitive to the not only to the cubic self-coupling, but also to the quartic self-coupling in the Higgs potential. Okay, so then in view of the law of cross section I already described in the previous slide for triple Higgs production, we are going to follow the following storyline. So first, we are going to study the feasibility of actually detecting triple Higgs production in the FCC within the standard model. So here is just the standard model, nothing else happening. And then we are also going to explore what happens if you add new particles to the standard model. So how triple Higgs production is affected in this case. And for this second situation, we are going to consider two setups, the FCC again, and the high-lumi LIC. So again, the high-lumi LIC cannot detect the standard model situation, but it may be that once you put extra scalars, the cross-section gets enhanced. We will see that that's indeed the case. Okay, so far I have talked to you about triple Higgs production. Before continuing, let me mention the following. You can see in these diagrams that in the standard model, triple Higgs production is actually loop-induced. So this explains in some sense why the cross-section is small. So far, I have only talked about triple Higgs production itself, but the Higgs is not stable. The Higgs subsequently decays. So then, what you find in the detector is this final state X that results from the subsequent decays of the scalar Higgses here. In this table, I am showing possible final states. And the branching fraction for this transition is also quoted in this table. One of the interesting things is that the state where you have 6 P's, the one that is highlighted here, has the highest branching fraction by far. Okay, so that's nice. I mean, you are looking for processes that have a high probability to be detected in order to, I mean, our aim is not to detect 6 B's, but the triple Higgs production. But through this channel in particular, we can actually reconstruct triple Higgs production. Once more, we look at this final state because it has the higher branching fraction. Fine. However, there is no a free lunch. So there is a high probability of produce this final state for the signal, but you have high backgrounds. That's the problem. So you look at processes other than your signal process. Our signal, this is our signal process. Triple Higgs going to X, where this X is going to be 6 B's in the final state. And a 6B final state can come from other sources, can come from purely QCD processes. And you can see that the cross-section of purely QCD 6B final state is large. We are talking about 52 picobarns. So remember that the cross-section for our signal process in the standard model in the high-lumi LIC is not 0.05 femtobarns. So here we are talking about picobarns. So this is 3 orders of magnitude above the femtobarn itself. But in the standard model, we are talking about not 1 femtobarn, but 0.05 femtobarns. So this is this overwhelms the signal in the high-lumi LIC. In the FCC, the cross-section for the signal is about 50 femtobarns. Still is 3 orders of magnitude below this quantity. So again, triple Higgs production through 6 B's in the final state has the higher branching fraction I showed in the previous slide. However, there are other processes that can mimic this final state that have a very high probability of occur. And all these processes are just background for us. Here are other examples of possible final states that can also mimic this 6B state. But you can see that in all the other cases, sorry, the cross sections are far smaller. Okay. In addition, you have this collection of states as well. Anyway, so all these are possible backgrounds, but the main problem is 6B is coming from purely QCD processes. Okay, so now this is a Monte Carlo study. So then we simulate a signal and background using Monte Carlo tools in the computer. So here are the details of this computer analysis.
Can I make a quick question, Gilberto?
Sure,
so so this background, I mean, aren't you looking for BB bars which are have invariant mass of the Higgs mass, and this is completely different story, no? Is that correct?
So you are asking me if I consider these pairs, the invariant mass is close to the Higgs? Is that what you're asking?
No. So your signal should be 3 pairs of Bs, so 3 BB bar pairs, which have each one of them have invariant mass of 125. No.
Exactly. So the idea,
this is not going to happen with this background, no.
Sorry, please.
This is not going to be the case with the background. No, the background is going to be
no, indeed, and I will not talk about that later. So that's one of the expectations, right? So the idea is that each Higgs here decays into a pair BB bar. Correct? So you have 3 Higgses, you have 3 pairs BB bar. If this state comes from pure background, pure QCD processes, then if you take the pairs, you expect that statistically you get a distribution, and that distribution is not big in 225 giga-electron volts. So in that sense, yes, the invariant mass is one of the observables that you can use to discriminate these 2 processes. So that was your question, Javier?
Yes.
So yeah, I want to talk about that later. Indeed. So you expect that the profile of this, of the invariant mass for pairs of Bs coming from other processes that are not the signal, the distributions are not big at 125 in particular for the invariant mass in BB bar. But randomly, you can have processes where this happens just by a random fact. Again, you have a distribution. And the center is not going to be 125, and you can use these to discriminate, to get rid of backgrounds, but it's a bit more complicated than this. That's one of the observables. You have to use other observables in addition. I'm going to talk about that soon. Any other question? Okay, well, then I continue. So then the main source of background, based on the discussion I have given so far, it's going to be 6 VGs. And in order to make statistically meaningful statements, you need to simulate a high, a number of events that is high enough. Actually, simulating 6 Bs in the final state for QCD processes is already challenging. So there are 2 stages in a Monte Carlo analysis. So, okay, we can say 3 stages. In one of them, you simulate the processes at a partonic level. So meaning that you produce proton-proton going to 3 Higgses with stop happening in the middle. And these 3 Higgses go into 6 Bs. But we know that the big quarks hadronize. So then the second stage is to shower all the previous simulation. So the first simulation is a partonic one. So you look at the Bs as particles, independent particles. The next step is to dress this isolated piece. So you hadronize them, so they form bound states. So the first stage is done with a program called MATGraph. The second stage is done with Herwig, and even the partonic simulation of the 6p final state is already challenging. So we use, so this is not something that is going to run in your laptop. You can make a test. You can download MATGraph and try to simulate PP going to 6Ps, and you will see how the program struggles to get that state. So we use some tricks to do this. In particular, we use clusters to produce the samples. So it takes about 1 week to generate a high enough number of events in the cluster. The clusters, we use the cluster. So this project was done in 2 parts. So the first part was done in Amsterdam. So we use the cluster at NICEF. And the second part was done here in Siegen. So we use the cluster here at the university. And then the third stage, because I talk about 3 stages. So the first one is the partonic level simulation. The second stage is the hadronization. And the third stage is the analysis, where you try to come with an analysis that can discriminate Singlet from background, using tricks like the ones that Javier mentioned. You can use the invariant mass, for example. Here is precisely, so this slide is devoted precisely to the analysis. So then you simulate the processes, and you have events in the computer. And then what you are asking for is that these events should contain 6 B-jets. So when the bottom quarks hadronize, they produce jets. And there are ways of identifying whether or not these jets come from the hadronization of a B quark. So then, if it turns out that your jet is consistent with a B quark, then you tag this jet as a B jet. So we need 6 B tag jets. Okay, now the second criteria was exactly what Javier mentioned. So what you do is you do pairings of these 6 B tag jets. You try different combinations because you are not sensitive to the charge. In principle, you have BB bar, but you only see a jet. You are not sensitive to whether you have a B jet or an anti-B jet. So then what you do, you play with the combinatorics. It's not so complicated. You only have 6 B jets. And then you define this chi-square function. So this M capital tells you the invariant mass of a particular pairing of B jets. And this little MH is the 125 GeVs that coincides with the mass of the standard model Higgs. Then you can impose some bound on this variable to discriminate signal from background. As I said, once you hadronize, you get distributions, for example, for this chi-square. So it can happen that just for a random fact, the background can mimic something that is very close to the mass of the Higgs. So then you have to impose some cuts on this variable in order to get rid of background events. Because you don't generate you generate distributions. So okay, now let me see. All right, so this is the construction. This is how the basics of the selection analysis. In addition, we impose cuts on different kinematical and geometrical variables. So here are the cuts that we use during the analysis. Again, this analysis is done in the FCC. So then we have cuts over the transfer momentum. We have geometric cuts for the rapidity. We also put geometric cuts on the different of the possible candidates to Higgs and so on. Okay, once we do the analysis, we can see how well we discriminate signal from background. So the idea is that you impose the set of cuts that we just described before. You apply this selection analysis to your signal sample and to your background sample. And then you assess how many of the signal events pass the selection criteria and how many of the background events pass the selection criteria. And then you compare these two numbers, and the way of comparing these two numbers is through a quantity called significance. The significance is the root square of the number of signal events that pass is the number of signal events that pass the criteria, the selection criteria, divided by the root square of the background. And you expect at least 2 sigmas. We find that with our setup, you can achieve 1.7 sigmas. That is very close. So this is the threshold for having a meaningful result. So indeed, for the purely standard model case in the FCC, we can reach something that is very close to 2 sigmas with the previous setup. Okay, but you can also think in more general settings. So you can take your triple and quartic couplings, as in the standard model, and introduce some deformations by some quantity C3 and D4. And then, in a model-independent way, do analysis for BSM situations for these more generic potentials, and repeat again the simulation, the selection process. And indeed, you can increase the significance for BSM values of the triple and quartic coupling constants. In particular, for the quartic, here we have this diagram where the significance can go up to 5 sigmas. But of course, I mean, there are large uncertainties because we are talking about the FCC. Okay, so then based on these results, we can conclude that it's feasible to find triple Higgs production as in the standard model in the FCC, considering the current setup. Right. Are there any questions up to this point? Okay, so I guess that means no. Right, so let's go to new physics situations. We can, for example, add an extra scalar to the standard model Higgs potential. So then this is, for instance, the potential of what is called the X standard model. So you add an extra scalar. And now you look again at triple Higgs production in view of the new scalar. So the first thing you have to do is, for instance, to expand this new scalar around its vacuum expectation value. And then you go to the physical basis. So the physical basis is done in terms of this H1, H2. And if I remember correctly, here the H1 is the standard model Higgs, and H2 is going to be the BSM state. One of the differences between this setting and what we have previously for the standard model is that now triple Higgs production can occur at 3 levels. So I showed you in the second slide that in a proton-proton collider, triple Higgs production, as in the standard model, is mediated by loop diagrams. So that's one of the reasons why it's quite suppressed. So now the triple Higgs production can be induced at 3 levels. So then the cross-section can be increased with respect to the standard model value. Okay, so let me go back quickly again to the to the potential. You can see that there are different constants. This is A's and B's. And depending on the values of these constants, you have different materializations of this model. So in this paper, they used this model to do a bit of cosmology, and they found a set of values, a set of benchmark points for the parameters of this model, such that you satisfy all the first order electroweak phase transitions. And once you find those set of parameters for the A's and the B's, you can fit the Lagrangian and simulate all the signal as we did before for the purely standard model situation, and do an analogous analysis as the one that I described at the beginning. Okay, and then you, after applying the selection analysis, you count how many signal events pass the selection, how many background events pass the selection, and you calculate the significance. The significance is going to be given by the signal over the root square of background, and you expect that that significance is at least 2, so that's 2 sigmas. Okay, so in this new scenario, for these different benchmark points, we have significances that are all above 2 sigmas. So again, in the FCC, you have an extra-scalar. The chances of spotting triple Higgs production are optimistic based on the current setup for the FCC. Okay, so nice. I mean, this is not unexpected. Once you put BSM particles, you can indeed enhance the possibility of detecting a triple Higgs production. I am addressing that point with a very concrete scenario here. And this scenario can have different materializations depending on the values of the constants. And that's the story in this slide. Okay, so any questions before going to the third part of the talk? All right, none so far. This is the third part of the talk. So up to this point, I have studied triple Higgs production as in the standard model in the FCC. I didn't describe this for the high Lumi LHC because we saw that the cross-section is very tiny. So then we went to a future collider and we found that it may be feasible to find this triple Higgs production through 6 Bs in the final state. That's the highlight. So it's 6 Bs. You can use different channels, but in this talk, I am referring in particular to 6 Bs. Now, before touching this third part of the talk, I would like to mention that during the selection analysis, we are never using machine learning. So if you use machine learning for discriminating signal and background, the results can just get better. So you can see that our thresholds are in all the cases very close to 2 sigmas. And we are not using machine learning yet. Fine. Here comes the third part of the talk. So now the question is, are there any chances of seeing triple Higgs production in the high Lumi LHC? The answer is probably, but you need to include again new physics particles. We'll already analyze the situation of new physics for the FCC with one scalar. So what I'm going to talk now is about enhancing the triple Higgs production for detecting triple Higgs production in the high Lumi LHC by using what is called the 2-real standard model. So then what you do is you add 2 extra scalars, S and X, to the standard model Lagrangian. So the purely standard model situation is encoded in this phi capital, but now you have 2 extra scalars, S and X. And you write the potential. And the potential can have a more elaborate structure than the one I'm showing here. In order to get rid of parameters in the general setup, in this particular model, two discrete symmetries are introduced, the ones shown here. So you demand that the potential should be invariant under these discrete symmetries. And once you do that, you cut the number of terms that can be in the potential, and the result is what is shown here. Okay. And again, what you do is you write these new scalars in terms of physical, well, not yet physical. You develop the vacuum expectation value. You expand these two scalars around some vacuum expectation value Vs and Vx correspondingly. And then you go to the physical basis. So the physical basis is given in terms of H1, H2, and H3. So this model is described in terms of the following parameters: the physical masses of the two new scalars, the rotation angles, that there are three, because you have to rotate these three-dimensional vectors into the physical basis, and the vacuum expectation values of the new scalars. So in total, you have 7 new. Well, that's not true. Yeah, seven new parameters. Okay. Now you are going to identify H1 with the standard model Higgs boson. So in that respect, the mass of the scalar H1 is already fixed, 225 gigaelectronvolts. Okay, so in this new model, there are, as I said, 7 independent parameters. The mass of the Higgs is already fixed. Okay, the mass of the Higgs in the standard model, H1, little H1, is already fixed, and you can put different values for the other entries. Okay, so in this paper, my collaborators look at possible values for the free parameters in such a way that you can enhance triple Higgs production without breaking any of the current constraints from theory and experiment. So triple Higgs production in this new scenario can occur through this diagram. So you identify H3 with the heaviest scalar, and the second heaviest scalar is going to be H2, and the standard model Higgs boson is going to be the lightest one. Then you have this hierarchy of masses. So then what is going to happen is that the heaviest one can decay into standard model Higgs boson and H2, and H2 can subsequently decay into 2 standard model Higgs bosons, and each Higgs boson, standard model Higgs boson, decays afterwards into pairs BB bar. And here, this is how you achieve 6 bottoms in the final state. Once more, this is a 3-level process. So it's expected that you are going to have enhancements with respect to the standard model. Standard model gives you triple Higgs production, 3 H1s, but you need loop processes. Here is what you find is a purely 3-level situation. Okay, so then what you do is you consider the values again that my collaborators found in a previous paper for enhancing triple Higgs production. You find that basically everything is fixed up to the masses of the new scalars, M2 and M3. So you want to enhance triple Higgs production. The angles and the vacuum expectation values are very constrained, but the masses can still vary within these ranges, the masses of the new scalars. So then what you study first is how the cross-section behaves with respect to the masses of these new physics states. Okay, and then you find that if the two new scalars are actually decaying on shell, this is precisely what is happening in this region, then the cross section increased dramatically. So okay, so then in order to have enhance on triple Higgs production in this particular scenario, the two scalars have to be on shell. Once more, you put this model in MathGraph, you produce the partonic samples, you hadronize the samples, and then you do the analysis, and you calculate the significance. The threshold for the significance is again 2 sigmas, and we select, I mean, it would be nice to actually do an analysis for all the points in this region, but you cannot do that. You have to select a set of benchmark points inside this region. Another thing that I haven't mentioned is that not all the on-shell region is allowed. You have this wedge here and this black area here that are actually excluded by boundness from below constraints and from perturbative unitarity. Okay, so then you take some points between the allowed region, and then you do the simulation, you do the analysis, you calculate the significance. And then you find that in the points that we consider within the on-shell region, we can indeed achieve a significance that is at least 2 sigmas. So this looks good. That means that the discrimination between signal and background is optimistic. Of course, 5 sigmas would mean a discovery, but this is again a Monte Carlo analysis. But you can achieve at least 2 sigmas in all the cases. So you can test different luminosities. This setup is for the LHC. The previous one was for the FCC. Now this is for the LHC. What is changing is that we are looking at an extended model where you have 2 extra scalars besides the standard model one. Right. So then the situation is optimistic. And this leads me to the end of my talk. So then it seems that triple Higgs production, as in the standard model, cannot be proved in the LHC because it has a very tiny cross-section. However, in the FCC, the situation ameliorates. The 6B final state is a good candidate. At least it seems like a good candidate based on the different scenarios that I described during the talk to identify triple Higgs production. And if you put extra scalars, in particular using this 2 real standard model setup, you can actually be able to prove triple Higgs production even in the high Lumi LHC. The other interesting thing is that with triple Higgs production, you are not only sensible. You can not only prove triple Higgs coupling, but also the quartic Higgs coupling. So that's quite interesting. That's basically it from my side. So I hope this was informative. Okay, thank you.
All right, thank you, Gilberto. It's nice talk. Does anybody have any questions?
Hello.
Looks like no one sort of anything quite yet. I'll start with something. So yeah, so they're searching for the standard model triple Higgs coupling, or the HHH in the standard model. There's 6B. Like you said, it seems like even at the FCC, right? This is not super great prospects, right? You get
in the LHC, yes,
significance, yes. Yeah. Like are there other ways, or other people thought about other observables or something at either at the LHC or at FCC for measuring this triple Higgs, standard model triple Higgs coupling?
Please repeat. So, there are any other observables that can be used?
Yeah. Is this the main one people think about? This like this 6B final state, or are there other observables that you could use to test the Standard Model triple Higgs coupling?
Yeah, I mean,
Do you know
so indeed, so people can look at this in different different final state channels. So, for example, there are analyses considering 4Bs and 2Ws. So here the idea is that 2 Higgses go into 2Bs, and the last Higgs goes into 2Ws. Again, one of the disadvantages here maybe is the cross section, but people have looked at this. Let me see. Well, actually, we don't have a reference for this one. So sorry, but for BB, so for Bs and 2 taus, there is this analysis, for example.
Okay, is that better? Do they get better significances on the couplings from that analysis compared to the 6B?
I mean, the threshold is always 2 sigmas, right? If this is done for the FCC, it's also, I mean, you cannot make, well, you can make refined statements. You can say, maybe I can get 4 or 5 sigmas, but the threshold is always 2 sigmas, especially for the FCC. There are large uncertainties. I mean, it's a future collider, so there are large uncertainties over different quantities. So then 2 sigmas is always is a good reference to what can happen. So if you get 3 sigmas, I mean, this sounds good, yes.
To really have an idea of what you could do.
But the threshold is always 2 sigmas. So in that sense, if you get, for example, I mean, in some of the scenarios I was showing, so some of the significance can go far above 2 sigmas. But again, saying that, relying on that now is not the best thing to do. So once you reach 2 sigmas, that's good. But of course, some of these channels can be cleaner than others. That's true. That's true. I mean, the advantage of 6Bs is that it has the largest branching fraction. But again, you are facing a background that can also has a very large cross section. So then you have this compromise. I mean, what you can find is that in some of these channels, you find backgrounds that are easy to suppress. That's true. And in that sense, yeah, that's going to be reflected in the significance. But I mean, taus decay. So I don't remember exactly how optimistic was this, how optimistic were these analyses. I wouldn't be surprised that, for example, here you can get a better significance. But again, once you go up above 2 sigmas, or close to 2 sigmas, that's enough to say, yeah, there seems to be an optimistic channel to look at in the future. Yes.
Okay, it's kind of the it's not they're not doing kind of precision studies yet. You're just saying, okay, is this a plausible thing to measure?
Yeah, exactly. So you look, but again, for sure, there can be channels that are more cleaner. So I wouldn't be surprised that, for example, this is cleaner. Okay, the problem in this channel, for example, is that you are thinking in W's going to leptons, and then you're going to generate neutrinos. So then you have to reconstruct the neutrinos, and reconstructing neutrinos is not a clean business. You have to make assumptions. So
yeah, I guess that's probably that way the W is all the taus, right? You're always going to end up with
the taus also decay, right? So that you have neutrinos. So it's again, there is always some compromise. You can see again that the branching fraction is also tiny, but again, the leptons are easier to spot than so muons are easy to find that reconstructing the Higgses, for example, using these, but now you have the neutrinos. So you have subtleties going on.
Okay, thanks.
Mm-hmm.
Does anyone else have any questions? I can't see anyone virtually putting their hands up or anything. So thank you again, Gilberto. I'll just find the button.
Okay.